Welcome to this lecture, 19th lecture, that we will see network analyzer calibration with the help of signal flow graph. Now, network analyzer we have introduced in this course, that it measures scattering parameters of a network. That is why it is a very important instrument in measurements. Now, in network analyzer, when we discuss its architecture, we have seen that the measurement of scattering parameter, that is reference plane dependent. If you change the reference plane, the network analyzer the S parameter gets changed. Now, in the measurement network analyzer, its reference plane is quite inside the instrument. That is not accessible to outside, but in outside, to connect the DUT from the ports, we connect some connectors, we connect some transitions, we connect some cables, etc., and then the device that we want to test, that is put. So, this extra thing that shifts this extra connections, connectors, cables, that shifts the reference plane, and that is why the measurement includes those loss and phase delays that are obviously present in any cable, connectors, etc. And so, there is some error in the measurement. Now, as network analyzer is very precise measurement, so these errors become significant. Now, in microwave bench, etc., the measurement itself is not so precise. That is why there even these errors caused due to that change in reference plane does not come into such prominence, but here in network analyzer, since it is a very precise instrumentation, so this needs to be corrected. That is done by putting all these errors, etc., errors, phase delay, etc., into a box that is called error box. So, error box represent all these lossy or error effects. Now, that error box is characterized by S parameter. So, if we are aware that there is an error, we can characterize that error, that we will see how it is done. And in that, finding that error box S parameter, these are assumptions made, but it can be always, if the assumptions are not valid, you can rework that at the two ports, whatever extra thing you connect, that error causing connectors, etc., they are symmetric and they are having same characteristic impedance. Now, if not, you know how to handle different characteristic impedance. In the generalized S parameter, we have shown you that. Also, we assume error boxes identical for both ports. Now, that means the both port there are identical connections. If not, you need to change some of the formulations, and also error boxes are reciprocal. That means, we are not using anything in that connections and transitions, etc., which is non reciprocal. So, error boxes also are reciprocal. Now, calibration of network analyzer, the simplest way, which in earlier days used to be done, that if you have three standard loads, one was short, one was open, another is matched load, you know that what is their behavior, what is their reflection coefficient at the loads. Short will have a -1, open will have a +1, matched load will have a 0. So, by that you can found. But getting the standard loads, you see, I can design a short, I can say that reflection coefficient is -1, but in reality, if you want to fabricate a short, it is a metal plate. Now, that has a thickness. Now, whatever you see that it should not absorb anything, but generally some waves go inside. So, the complete reflection you do not get. Also the reflected wave's phase is 180 degree opposite to the incident wave's phase, that is not always true. So, there are some imperfections. Now, making a open is quite a problematic thing. You know, there is a transmission line by which actually we convert a short to an open, and now that thing is very precise at a particular frequency, always it is not same, and match load also that we expect it is absorbing the whole thing, whole power, but nothing is coming out, but in reality something comes out. So, any standard like that is imperfect. Obviously, it is very that imperfection is small, but there are some imperfection. So, later people come up with the things that okay, we need those some loads, but they are not so correct standard loads. That calibration procedure, which is a modern calibration procedure nowadays used, that is called TRL calibration. Now, TRL, T stands for through. Through means a through line, as we were showing in directional coupler, the through line. So, through, reflect, are line L. Now, what is through? Through means just connecting port 1 and port 2. Instead of connecting that DUT, if you just connect the accessible port 1 and accessible port 2 of the network analyzer directly together, that is called through connection. Obviously, the male female matching will be there, that is why there is some thing there, but through. Then reflect means you use a high reflected load. What is a high reflected load? Either an open and short, both gives high reflection, both value are near 1, one is -1, another is +1. So, you take any, and it need not be exactly -1 or exactly +1, it is called, that is why it is called reflect, not short nor open, that it is a high value of reflection coefficient. And that value also you need not know, that what is the reflection coefficient of that. It should be high, so that you get good amount of reflected signal, but its value actually as a byproduct of this calibration it comes out, that what was that gamma L value. Similarly, what is a line? It is some length of transmission line. So, since the ports are generally coaxial, so it is a some form of a coaxial line, but in waveguide calibrations it can be some length of waveguide line. Now, here also what is the line length you need not know, or what is the propagation constant of that line, that also you need not know. The line need not be lossless also, the whole gamma, that means the propagation constant into L, that thing comes out of the as a byproduct of the calibration. So, TRL calibration is so good that your these loads or other things are not so perfect, but it is not required to be perfect also, but it finds out those values in the whole process. So, this is called TRL calibration. Now, first let us see the block diagram of a through connection. Now, you see that port 1 and port 2, they are put together. Now, obviously, this is your actual inside reference plane of the network analyzer, which is its ports inside, and these are, since you have connected something. So, there is an error box S, as we said that in both side we have assumed error box same. So, yes, also due to the nature of connection, you see the instead of S you can also have transmission parameters both side, and you see that if you call this side ABCD, this side you should call DBCA, because the things are here coming from one side, here from another side. So, direct connection of port 1 to port 2, that is called through connection. Now, in the signal flow graph, what will be this? So, you see that we have this S matrix, we know this is a error box S matrix. We are assuming same S matrix here, only thing is A 2 B 2, this is A 1, this is A 2, this is B 2, this is B 1, that is why these directions etcetera they got changed. And inside you see through means directly the transmission from this point to this point is 1, this point to this point is 1. There is no transmission line also, it is just 2, that is why these two ends are connected by 1 of this through connection. And now, reflect connection, you see that you have a high reflection load, that is why port 1 is getting high reflection coefficient. Similarly, in port 2 you connect high reflection coefficient. So, a load with large reflection coefficient, as I said, nominal open and short will do, not necessary to know your gamma L value. Now, this part we are calling it as R matrix, this is reflect. So, R. So, these error boxes they will now be an R matrix, like in the previous case this one when we are connecting T, that we are calling this whole error box and this connection everything we are calling T matrix. Here in the reflect case this whole thing we are calling R matrix, and this is the signal flow graph, that port 1 side, port 2 side and gamma L in between. So, this is the two disjoint graphs here because of the reflect connection, that the port 1 that is getting fully on its own, similarly port 2 is getting on its own. Now, this is block diagram of line connection. So, line means you see a transmission line, we are assuming not beta, it is gamma. So, loss is allowed, it is a length L. So, you see line connection, a matched transmission line between port 1 and 2, as I said not necessary to know length and not necessary to be lossless also. This whole these two error boxes and this line together, that we will designate as an L matrix. So, if we know the T, R and L matrix, then we can find this error boxes is completely, that we will show now. And this is the signal flow graph of line connection, again two port networks, between them this line. Now, come to the T matrix. So, this was the signal flow graph here, we will apply the Mason's formula. So, what we are trying to find when we are trying to find the T matrix, basically this T matrix all are something like S matrix, scattering parameter. It is together scattering parameter of the error boxes two side and then the through connection. So, this T 11 will be B 1 by A 1 when A 2 is equal to 0. That means, this side matched, then how much you are getting. So, that means, I will have to come from this independent variable to this dependent variable. So, what are the paths by which I can do? One path is definitely this one, that we are calling P 1, and that value of this path is S 11. Another path is, you see this one, then I can come back. So, this is another path. that we are calling S12, 1, S22, 1, S12 all products. Is there any other path? Can I come like this? But there are no coming. So, but can I come like this? That we have already done, but this one we cannot come. So, only there are two paths for coming from this side to this side. Now, is there any loop? You see, this is not a loop because I cannot come here. This is a loop. So, this is a loop. Again, this is not a loop. Now, so there is only one first order loop, that is 1 S22, 1 S22, that we have written L1 is this. Now, obviously, since there is only one L1, then there is no L2, L3, etc. Now, let us also see whether L1 is P1, that means first order loop non touching P1. P1 is this path and this is first order loop. So, obviously, they are non touching. So, what is the value of that? That will be your this loop, its value was this. So, L1 P1 will be S22 square, the value of this loop, and L1 P2, P2 is this path, but this loop is touching that path, that is why L1 P2 is 0. So, with this you can put T1 values by Mason's formula, that P1 is S11 into 1 minus L1 P1, that is S22, plus P2 1 minus L1 P2, that was 0, and here 1 minus sigma L1, there are no L2, L3, etc. So, this. So, that by this thing, this is becomes your T11 in terms of this. This we are calling first equation. Then determination of T12. T12, what is the definition? A1 should be now 0. So, we are putting A1 0, and we will have to find B1 by A2. B1 is this, A2 is this. So, from A2 to B1, how we can come? One path I am seeing directly. So, P1 is S12, 1, S12. Is there any other path? Can I go here? No, this is blocked. Then this is, then it is blocked. So, there are no other path, only one path for coming from here to here. Is there any loop? Yes, that old loop, that value I know, but my path and this loop, they are touching. So, L1 P1 is 0, and obviously, there are no L2, L3, etc. So, we can put this value S12 square 1 minus that L1 P1, that is 0. So, this we are calling second equation. Then T21 and T22, you see the signal flow graph. By symmetry we can say that T22 is equal to T11, and by reciprocity, the whole thing is reciprocal. Error boxes also we assume to be reciprocal, obviously through connection is reciprocal. So, by reciprocity T21 and T12. So, no extra information is coming from this, but we know now T matrix completely. That means, through, when we make through this T in terms of these S parameters, we know. Now, T matrix we can measure. Now, you see this determination of R11, the reflect case. So, there this is the signal flow graph. Now, R11 is B1 by A1, that means I will have to come from here to here. One path is directly this. So, P1 is S11, another path is this, you see this. So, S12 gamma L S12 P2. Now, loop Where is L1? Is there any L1? Yes. This is the loop. You see, this is a loop. There are no other loops. So, gamma L S22 and L1 P1, does it cut? S11, S11 is this, loop is this. They are not cutting. So, L1 P1 will be this L1 value. L1 P2, what is P2? This, but the loop is this. So, they are touching, that is why L1 P2 is 0. Now, with this you can put it in Mason's formula, R11 will be this, that will give you this equation gamma 3. Then as port 1 and 2 decoupled, so obviously we can say R12 and R21 they are 0, because signal flow graph itself is cut. So, no signal can come from 1 to 2 or 2 to 1. So, R12 and R21 will be 0 and the whole thing is symmetric. So, you can say R22 is R11, but that does not, this determines the complete R matrix, scattering matrix for R connections, but that does not give us any extra information, extra equation. Then the last one L11. So, there again L11 means B1 by A1. So, A1 to B1, one path is P1, another path is this, S12 e to the power minus gamma L, S22, then e to the power minus gamma L, S12. So, there are two paths. Is there any third path? I can go here? No, because this is not allowed. So, there are two paths. Now, is there any loop? Obviously, this is a loop, clear. So, e to the power minus gamma L, this e to the power minus gamma L into S22. This is a loop. Any other loop? You see, this is not a loop, this is not a loop. No S parameter can be a loop, 2 port S parameter. Okay. Now, L1, is it touching with P1? This loop is not touching with P1. So, L1 P1 value will be this loop value, that is e to the power minus gamma 2 gamma L into S22 square. Now, this one L1 P2, but L1 P2 is this and this is the loop. So, they are touching. So, L1 P2 is also 0. Now, we can put it the values will be something like this. That gives us fourth equation L12 determination. L12 is what? B1 by A2, B1 by A2. So, there is direct path is there P1, S12 e to the power minus gamma L, S12. Is there any other path? I can go here, but then we will get stuck. I can go here, I will get stuck. So, there are no other path. And is there any loop? Obviously, this loop last time also we have seen L1 is there, but L1 is touching this loop. So, in this case L11 will be 0. So, this is our value of L12. So, 5 equations. So, we have got, you see this in terms of the error boxes S12, S11, S22, etc. We have got these 5 equations. Now, when you see in all these cases, the network analyzer is measuring this L matrix for line connection, R matrix R connection, and T matrix T connection. It is measuring because these are its internal planes. So, this whole thing it is measuring, and so we have found that from that measurement it will find T11 is in terms of S11, S12, S22. So, S parameters are 4 S parameters, and we have 5 such equations. We have 5 such equations. So, they can be solved. This by symmetry, we have 5 equations, we have 5 unknowns S11, S12, S22. Due to the error box reciprocity, we know S12 and S21 will be same. So, S21 is not shown here. So, S11, S12, S22. 3 unknowns. Gamma L is an unknown, that means the load that we have connected in case of that reflect connection, that its reflection coefficient, and in case of line the gamma L. So, these 5 unknowns are there, we have 5 equations, they can be solved. I am not going into that how to solve 5 unknowns, 5 equations by proper manipulation. That manipulation is a long one, but you can solve it. So, by that you can determine this. If you determine these 3, basically you are determining the complete S matrix of the error box. So, now you know error boxes. So, you can find out from that error boxes what is the actual, when you will do actual measurements, you know that with your DUT you will have that error boxes. So, you find those error boxes, and also in the process gamma L of the reflect connection gets determined. That was not your objective, but you see that what type of load you are using. Suppose your that load is not very good, because if the signal coming low, then there are the sensitivity problems come. So, that you can check. Also you can get your through connection, what is the gamma L of that. So, you see such a nice procedure that you measure by 3 such TRL connections, the S parameter you measure, network analyzer measures, then it finds out that S by this mathematics, and then it now knows error boxes. So, actual measurement time it can correct that for those errors. So, I think that is, you see this type of complicated things with the help of signal flow graph, it got very simplified. That is why it is a very elegant and useful tool for microwave designers. So, with this we complete all the lectures except the last tutorial. So, here we have seen 3 main tools: Smith chart, scattering parameter, signal flow graph, but we have seen lot of applications of that. We have seen impedance matching techniques, we have seen the network analyzer measurement, microwave bench based measurement, network analyzer, we have seen the network analyzers calibration also, and also we have seen some useful devices, their scattering parameters like directional coupler and magic T, which are used heavily in microwave circuits. So, with that this theoretical part is completed. Next we will have a tutorial to exemplify these signal flow graphs and some of the S parameters. Thank you.